Okay, my friends, cosmic shocker du jour. This is our sun, and these are the particles that surround it in its magnetosphere and its corona. They just did a fly-through of this the other day and showed what particles really exist in there and the actual vapor coming off the sun. I call it atomic vapor. It's light. Now there's also actually these little particles. What do they look like? How do they react? I have been working with a guy called Cosmic Calliope, and we've been working back and forth. I've got a ton of pictures from him using all new techniques to visualize the sun and all the dipoles in space. I've shown you the other ones through all the magnetic fields and so forth. I'm going to show it to you right now again. And then we're going to dive deep into this new stuff because this is brand new and it is stunning. Hold on. Oh, my friends, I can't wait for this. I have been working with this guy, Mason. I have not talked to him yet, but he's been sending me pictures that are absolutely stunning. And these are actually real pictures of what's going on. He has some absolutely fabulous equipment. How he's doing this, I don't know. We're going to have a discussion momentarily. He may be chiming in right now as we're talking. But he's picking up all the dipoles that I have predicted. There he is. Hold on a second. Look at this. Absolutely stunning stuff. Here he is. Here he is. Hold on. Admit. Hold on. Hey, how's it going there, my friend? Wow, are you doing some stuff? Holy smokes. I got the camera running. Let me turn it off for 1 second. We can talk. Well, okay, my outstanding friends. This is like ice cream. I got Mason on the other end. So say hello, Mason.
Hey, everyone.
All right, he's a citizen scientist, and I'm telling you, this guy is doing things that CERN wishes they could do. I'm going to tell you that right now, and NASA and all of them. Because what you're looking at right there is something he's done with some little doodad. He's got a bunch of little things, and he's still using the CMOS in a galaxy. It was a Samsung, right? 23 or something?
Yes.
No, I don't. Yeah, okay, so I'm sorry, go ahead.
Yes, the Samsung Galaxy S23.
All right, and you are using that along with what else?
A 5-inch Newtonian reflector.
Well, let me ask you. Go ahead.
It's basically just the telescope that, rather than using a primary lens and an eyepiece lens, it uses a large mirror to reflect it to a secondary mirror and then into the camera sensor.
I'm sure that makes sense, but all right. Here's the deal. I am a material scientist. I understand energy. What I'm looking at here is a bunch of energy. Anytime you see white, it's energy. And anytime you see white, there's going to be black around it somewhere. Normally they're dipoles. If we come out here where we can get them separated enough, we can see every one of these is a dipole. You see what I'm going?
Yeah.
They're all dipoles. There's a black and a white. And I mean, it's just that's just the nature of these particles. And when they get further out, sometimes the white gets brighter, sometimes the white gets smaller. That's the key to the white. It can get big and it gets small. Now, let me ask you a couple of questions, Mason. First of all, these colors, are they representative of actual frequencies of light?
They are dialed up a bit because in order to pull the actual particles from the camera noise, which they call camera noise, is basically cosmic radiation hitting the sensor. So basically, it's not the visible spectrum that you would be seeing, but the wavelength itself is still the same, so it's just turned up. So even like for the sun, you know how our atmosphere scatters it into red. Our sun is actually, I believe they say it's white. So it's turned up a little bit so that you can see the actual particles that are being emitted from it, but they're still the same wavelength or still the same bracket. So it is representative. It's just the saturation is definitely dialed up.
All right, so I am holding up the visible the spectrum here. And I'm seeing red is way down at the low end of the spectrum, long radio waves into microwaves. Then you get into infrared, and then you get out to the ultraviolet and into the blue. So you start out here in the sun would be more, well, it's red. And it comes out to blue, which is an area for me that is highly energized above the source, which is the red. Would you agree with that?
Yes, I would agree with that. Yeah.
All right. So, oh, by the way, did I mention what Mason does? I don't think I did. You're going to school right now.
Yes, via Coursera online.
Okay, and which I did that, and I loved it. It was absolutely fabulous. And you're going for what now? Go ahead, tell them.
Just astronomy and cosmology, 2 separate courses.
Okay, and so your engagement with academia is to see what they say they have determined about the universe and about its construction, and what else? What else are they supposed to be teaching you? History or anything?
Some history, but predominantly just surrounding the theories, like even Einstein's constant speed of light and the expansion of the universe itself. But of course, I like to do my own observations, my own data collection after learning what they, teach you or tell you to say.
That's the best way to do it, because you cannot argue a side of anything unless you know the other side of what you're arguing against. So you're doing it the right way, and I think I would hope you're seeing what you should be seeing here.
No, yeah, definitely. Even in one of your recent videos I had watched, you were talking about how they say, there's nothing out there, and I really don't believe that. You could see like these fields interacting with each other, even in quote unquote voids in space. So it's definitely strange to see.
Well, even in 2013, Don Lincoln from Fermilab said empty space isn't empty. It's like the head of a root beer, or particles winking in and out of existence, on and off instantly. It's like a soup, and he's right. And where the soup collects as a dense layer, like where I'm going right here, right, it gets bright because there's too many interactions, and they're pushing everybody and pushing and shoving. The harder you push and shove, the more glow you're going to get. That's just the nature of it. So why is that band there, first of all? Secondly, look at this. You see this right here?
Yep.
You see this?
Yeah, I see it.
That's a double whammy. You see this darkness under here?
Right.
Darkness under here. It's like a tornado almost looking thing. And then it breaks into two. I mean, it's the stuff you could look at in these things, you could spend, your whole life looking at one picture almost. It's just stunning, the stuff you did. You wait to see the other shots where you were using the venturi, right?
Yes.
All right. I saw you had the 3 nails.
Yep.
All right. We're going to talk about that in a minute. Let's continue on with this. How did you get this very crisp outer border? What is that all about? Is that just where the particles energy stopped?
So I actually used this. I could show you. It's basically, rather than a normal eyepiece, it's a bit of a homemade lens that I use a clear crystal sphere in, so that way it directs the particles outwards rather than concentrating them like a normal eyepiece. And so I just take the photo right up against that glass bulb. So that circle that you're seeing is pretty much the sphere, this little glass sphere. I don't know if you can see clearly through here.
Well, I could see this very crisp line would be what you're talking about, the outside of the sphere?
Yeah, most likely the outside of this sphere or this border right here, just that black line, and then the particles are probably reflecting outward into the camera sensor itself.
Okay, so
right up against the glass.
All right, so these particles here then, what I'm starting to think is these are in the glass or something. These aren't out in space, are they? These when I'm going there?
Well, they would be out in space, and the image is just reflecting off the glass. So I believe that the particles outside of that rim are probably the ones that are leaving the glass, so to speak, or at least traveling that far. And the ones that you're seeing inside of the glass is like the collection of them hitting the glass, and then me taking a snapshot of that.
I'm a little confused, my friend. Let's start with the sun. In my model, the sun emits dipoles primarily, which is the black and white. And at the surface of the sun in this area, it comes off as what I call atomic vapor, which means that it's the white particles and the black particles are probably mostly separated at this point.
Right.
And it's and they are not in a dipole nature. They are in a vapor. Now, as that vapor comes out here, you get a condensation almost with the dark particles. And then they push against another layer out here, and you get another layer of glowy particles, and then dark particles, glowy particles, and then out here, this is what I'm confused about. Is this empty space, and would that same pattern of all these little tiny dots go all the way out here if you didn't have a bowl around it?
Yeah, they would pretty much extend all the way out to the edge of the camera.
Okay, all right.
Some other images I've sent that you might see that in.
Okay, that's the answer. Now, what do you make of these things down here, these little dipoles? Basically,
My best guess. Oh, go ahead.
No, go ahead. I don't know. I'm lost. Go ahead.
My best guess. I know that upon my research, I read that even just regular glass, or at least most glass, tends to stop. I believe it's ultraviolet light or certain frequencies of light. So maybe it's a shorter wavelength of light that's making it through the glass and hitting the CMOS sensor, because I still have it encased in a dark box so that there's no outside light coming in and causing reflections in the photo.
Okay, so to my thinking, you're saying that these little dots are photons primarily, right? Would you say that was a photon?
I would say so.
All right, and that would be a photon. That's a photon, and it's hitting some kind of pixel somewhere, right? Is that what you're saying?
Yes.
All right, and then you're limiting the field of vision to this circle.
Yes.
All right, good. That's what I want to establish, some ground rules. Now, for me, once again, every time I see something glowing, that's telling me there's energy there. And when it's glowing brighter than somewhere else, there's more energy where it's glowing brighter. So where is it glowing brightest is here. Well, let's take it this way. You're going to have a ring of basically magnetism, just like we have an ionosphere. This would be the ionosphere, or the corona out here of the sun. And the sun, you can see, is red. We're way up here in the blue, into the extreme blue region, which is extremely high energy compared to the sun, which is exactly what it is. Out here, it is millions of degrees Fahrenheit, millions. On the sun, they say it's only 10,000 degrees. That's why it's red. It's way down in the energy area. And way out here in the ionosphere, for them, it's the corona. And they just did a fly-through of that. Did you see that, Mason, the fly-through they did?
Yeah, the Parker Solar Probe, I believe it was.
Exactly, that's exactly correct. Did you see the vapor?
Yes, it was absolutely amazing.
Well, wasn't that something? And you could see that the vapor was just like vapor coming off of a coffee cup.
like steam, but
just like
fiery
steam. Yeah, like steam, but didn't push anything, didn't hurt anything, didn't weigh anything. And then all of a sudden, remember all the shower of particles came from behind?
Yeah.
Those were streaming through that steam. That's when you could see them. Otherwise, they're dark matter.
Yeah.
I'm telling you, this is a whole new world. This is opened up. And you know, we as citizens, I'm not the same as like Mason. I'm just doing this because I'm interested. And I found out that just does not seem to hold up as an interest to find answers to this stuff. So we're going to look for our own answers. Anyway, I'll get off of that kick. Now, I'm going to put this on hold 1 second, and Mason and I are going to find another thing to investigate, because he did some.
No, of course.
Yeah, he did some fabulous work with the Venturi. Hold on a second.
Sure.
Okay, Mason sent me quite a few shots, and they were stunning and very, very hard for me to determine. Now, I've looked at literally thousands of images of light when I worked with Rod for well over 10 years. And now Mason's got some tricky little doodads. He's making this stuff bubble out and these sharp curves and so forth. This was just taken with a shot from the cell phone, right?
Yep, same camera, same exact sensor.
Okay, and through what kind of Venturi? Was this through the nails?
Yes, through the same exact one that you had told me you guys had used back then, yeah.
Okay, 3 nails.
Just the 3 nails and 2 rubber bands, pretty much.
Okay, and was the Venturi right there?
Yeah.
Okay, so we're seeing that light coming through that set of nails. You don't see the nails.
No, because basically what I had done is I placed the Venturi in front of the laser, and then I had bounced the laser off of the surface and then into the sensor. So that way you don't have too much of the scattering. Because my goal was to reduce the amount of light so that you could potentially see more of the particles, but spaced out.
I got
like
you, yeah.
Clear image.
Well, that's amazing. Because I do see what you can see is some details that I missed in the other one. But look, if I'm right through here, you're talking about the Venturi would have been straight up and down here, right?
Yes, correct.
Okay, so the laser's coming through. Look at how bright this part is, and then it gets a dimmer, and then it gets bright again, and then it starts to pulsate. So it's already gone through the Venturi, and it appears to be, I would say, slowing down here, because back here you had see the separation between the green and the bright, and you see what I'm saying?
Yeah, I see.
Like this thing runs from here all the way down to here. That whole band is to me one frequency right now.
Right.
Now it starts slowing down here, and then all of a sudden you can see now the bands are just touching each other, the bright and the not so bright, the green. You see it?
Yep, I can see
and
it.
they're getting slower and slower and slower. That's pretty obvious to me. And now they're blended right back in to just being a background and not being bright enough to see.
Yeah.
Would you go along with that?
It's funny. No, yeah, I would definitely agree with that. I find it funny how it almost looks like a water hose when it loses velocity.
Well, it is.
And then the water starts separating. It's very, very close to it.
That is exactly what it is. It is exactly what it is. It's a Venturi, but a Venturi is nothing more than a nozzle. And it's for fluids or gases. Light is atomic vapor. It is a gas. All right, dipoles, when they're in a photon formation, they form a gas. And they are fluid, they're liquid. And they come through that Venturi, and they have to accelerate, and they can accelerate, but in this particular case, we can keep the black part away and just squirt the white through. They separate. They actually separate. The white comes through. Now, you have it where they're both coming through.
Yeah.
All right, Rod had it where absolutely nothing but the white was coming through in that one place. Now, if you tuned those nails, I don't know how he did it. I have no idea. Well, I know what he did. But he must have spent, I don't know how long you've spent, but he spent thousands and thousands of hours. I know he did. Because I did too, but I didn't do all hands-on like he did. I was examining things. But anyway, what do you see is going on here? What's this all about?
I wasn't entirely sure. I was hoping you would be able to help me out with that. I don't know if it's like a secondary reflection, whether it's off the venturi itself, or if it's just the camera lens itself, maybe the glass on the camera lens catching a different wavelength. I was thinking ultraviolet light, just because of the color of it. But I'm unsure.
It gets to be a much more corpuscular nature out here than here. There's a difference in texture, obviously, you can see that, and there is apparently some kind of, whatever this is, maybe there was a hair coming out of there or something and it got vaporized. I don't know, man. Things are so freaking crazy. You just don't know anymore. All right, let me show you something else that I saw that just freaked me out. Well, it all did. Because here's the key. Your stuff has the dark edge where it meets the white edge is always perfectly perfect. The white bounces around and so forth between, but the black always seems to, I don't know, I see a pattern between the two. But let me jump to something else. Anything else? You want to say anything about this one?
No, I definitely see the same pattern that you're talking about. I was wondering if it was due to the image stacking, because I know that the S23 uses something called adaptive pixel, where it basically takes multiple images at once and then stacks them for better sharpness. So I don't know if that's the phone software playing into that, or if that's the particles themselves.
That's the particle. Rod has the same thing. They did, apparently, I think the Galaxy S3, I think is what we used. S3, I think so. We had the same thing, because he'd take one picture and it'd be about 20 pictures in a row, and it was crisp. Woo! Absolutely flawlessly crisp. You've seen the pictures, right?
Yes, I definitely have.
Yeah, what do you think of them?
They look really good. That was one of the main reasons I had reached out, because I had stumbled across this when I had first developed some of these pictures, and was like, this is kind of strange. What are these fields? Why is it that I always see like the light and the dark together, or the light kind of like, moving faster than the dark? So, and then I stumbled across one of your videos with the same kinds of images, and I was like, oh, I gotta send this his way.
Well, I'm glad you did. I'm glad, and you got some fabulous stuff going on here. And you appear to, well, you got some equipment that I don't know anybody has that same equipment. I certainly don't have it. All I do is look out there, and whatever's out there, I see. Now, with some of these apps or whatever they have on these cell phones, I guess they're able to see, like the stuff that Dylan sent me. Yikes! You saw those, right?
Yes.
Now those. Go ahead.
Okay.
No, you go ahead.
I was gonna say, when it comes to like those types of images, I think anyone can honestly try and get similar results. I don't think it's necessarily about like the special equipment, but more so just having CMOS as like your starting point.
Right, exactly. CMOS is the key. CMOS was the key. You know that whole story, I'm sure. I've spouted off a million times. That we were picking these particles up in 2013, and we saw the same particles they were seeing at FERMILAB, but I don't know how they were finding them, but they were finding the exact same particles, only they were apart, and ours were together in the photons. Because we were using...
And then years later, they basically, oh, you can't do that, and then they're turning around and installing the same type of sensors.
Exactly. So CERN is shut down for a while and upgraded. And I argued with them about that CMOS. I said, we're using CMOS. Because they said, no, you can't see that, you're crazy, basically. I don't remember if they weren't nasty. I went to, well, you're going through Coursera right now, right?
Yes.
Yeah, well, I went through Coursera, I went to the University of Geneva. Now, I was able to interact with the professors there. I sent them my pictures and all this stuff, and I said, we're using light, and I showed them how it was accelerating. I showed them all the stuff. And what we were doing, and the venturi, and and here's the red, and here's the green, here's the blue, and they sent back, no, that's impossible. You're just seeing refracting, and they had all kind of little names for things. And I said, no, we're seeing light. And they said, no, you can't do it because they've destroyed the CMOS. I said, no, the CMOS is made to pick up these particular particles, which are photons, not paid for the stuff you had. They were sending out, you saw the stuff, they're sending out protons. And when they break, they might hit it with 1,000 times bigger particle, 2,000 times bigger. It's like hitting it with a Mack truck. And we're hitting it with a little, grain of rice, just barely. It's made to see the particles that is hitting it. And it does fabulously. I mean, this is just stunning stuff, man. All right, hold on a second. I want to show you the one that really freaked me out. Okay, I got Mason on the block here, and I want to see. First of all, I want to show you something. This is stunning, stunning, stunning stuff. You see down here at the bottom, the black surrounding the glow? Right. That's the high energy particle is in the center. You see how it waves, a perfect wave like that, like a piece of spaghetti twisting like that?
Right.
That's the spin of the particle creating these bumps. It's a spinner. And I said to him, how did you get this pattern here? And what did you say, Mason?
I just pointed it directly at the sensor.
All right, so what did he do? He pointed this spinning particle with black and white directly at the sensor, and what do you see? You see spinning black and white circles. Isn't that something? My God. Now, what can I take away from that as a dipole electron flood guy? Well, first of all, that was coming through the venturi, is that correct?
Yes.
And where was the venturi? Was it about here?
It's kind of out of frame for this one a little bit. Basically just right at the bottom, like where you were pointing out.
Way down here.
Yeah.
All right, well, that's about where, okay, that makes more sense. Because at this point, it's highly accelerated and it's doing that swish thing. You know what they call that? And I'm not kidding you, they call it the muon wobble. I'm not kidding you, man. No.
Sounds like a dance move.
I know, yeah, let's do the muon wobble, man. The Mudfossil muon wobble. That's what they're going to call it from now on. A dipole electron muon wobble. So we're wobbling away in here. Okay, so we wobble up here, and then all of a sudden we decide, well, we're starting to hit out of the wobble area, and we got to slow down. We move too fast. We got to make this moment last. So what happens here? Why are we seeing this gigantic ball? I don't think it's because of the reaction here. I think it's because of the reaction here exploding outwards, backwards, creating these layers of magnetic field, because this is what this is. And I'm going to show you what that is and how it's formed. That is moving light, brother. You just picked up something that nobody's ever seen before. Well, I take that back. Rod did see it too in a different way, and I'll show you his way. However, this is the spinning light. That's spinning light. and somehow it concentrates the light towards the center. Now, what's coming out the back is a dipole field. How that's doing that, I mean, well, let's think about this. We got light interacting now, slowing down, turning back into particles, and that particle is turning back into that black and white particle.
My thinking too is I've always noticed it almost seems to follow like the line in the field, like almost like it's on a track. Have you noticed that?
Well, yeah, I know. Yes, they do. The blue particles I can see going straight as a line, and they are spinning to the right, which makes the right part drift to the left. But this is something new. Now, you see these fields surrounding here?
Yeah.
That's nothing more than a magnetic field surrounding the black and the white. And there's the interface right there. And this light is forcing the bright to collide with a black.
It's definitely strange to look at, just even knowing like the wavelength of light and how I believe you guys did it with the red wavelength at first. I'm wondering if the fact that I used a green laser might be playing into it, because
well, the green laser, well, I could show you for sure what plays into there. The green laser is much faster spin than the red.
Oh, okay.
It's just a more faster spin. Now the red would be a fluffier field here. I'm going to show you, well, I'm going to show you this. Hold on. All right, Mason's going to be coming in any second now. This thing crashed on me, but what we're going to be looking at is the dipoles. They call them Diracs. Well, this is backwards. That's the energy. That's the matter. It's backwards. Oh, here he is. Hold on. Okay, my computer crashed on me, so I'm hoping it won't happen again, but, you know, life goes on. Now, Mason's here, and we're going to go back at this thing. Now, what I am going to show you right there, Mason, to me, that's light. All right? When it's this, when it's that, it's green. When it's this, it's blue. When it's this, it's red. It's exactly like a wave. All right, but it spins. Now, can I prove that? Well, I'm glad you asked. Because yes, I can. Here goes. All right, I got Mason looking at this. Now, he's a guy that understands light. Now, what do you see, Mason?
Well, it looks like almost like interference, kind of like that. I don't know if it's the dark particles kind of separating.
You're exactly right. They are interference patterns. Now, what is your traditional concept of an interference pattern?
Just in regards to if something's moving, or if like a surface is not as reflective. I'm not entirely.
Well, let me just explain what the traditional theory is on these separation zones, which they call interference. They say that light is a wave, and it flaps like a wave coming in off the ocean. And one going through the right slit, one going through the left slit. Their wave patterns just flop over and you go backwards and forwards like a wave pushing against another wave, and you get higher peaks and lower peaks. That's how they see this. It is not that way at all. It is light spins in a circle. Now, if you looked at it from the side, you would see a wave. I don't know, can you see me now?
Yep, I can see it.
All right, you see the wave. But when it's down here, it's blue real fast. When it's out here, real slow, and in the middle is green. Now, I'm going to show you, I can prove that too. Because I'm going to show you red and green at the same time through the same slit. All right, hold on. All right, these are two lasers, same time through the same slit. The slit's here. You can see how powerful the green is compared to the red. The red is just like a dull looking color. The green, very, very bright. Coming through the venturi, it's juiced up pretty good. And it's very, very powerful compared to the red. It just pushes the red. You see the red being pushed down to the underneath there?
Yeah, I can see that.
Yeah, it's just pushing it out of the way. Now, it does something else that I've never seen before either. It turns the red particles into spinners. All right, can you see that? They tumble, they roll like this, they roll this way.
Oh, okay, I can see it. Yeah, I see what you're saying.
All right, they're not supposed to do that. They're supposed to spin like a top. And that's what gives you upspin and downspin. There is no tumble spin. Tumble spin is being created here because the green is pushing the red out of the way and forcing it to tumble. It would never do that ever, 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 ever. They never do that. Even if they're going sideways or straight up in the air, they always are air oriented towards Earth. Now you can see how the green reconcusses way out there. And you can see the particle, the little box particle, right up there.
I can see it. Is that because of the wavelength of the green being much higher energy or much higher?
I'm not sure whether it's actually traveling faster or there's just so many waves compared to the waves of the red that it bounces into each. You know what I'm saying? Like you get 5 or 10 waves hitting one of the red, it sort of tumbles it. Because it's obviously pushing it out of the way. There's no question. There's a pushing and shoving going on here. That one's coming down and glowing because it's pushing any red that wants to get up. And there is a couple of red ones up here that just somehow managed to squeak up there, but they have no energy. And this pushed them right out of the way, tumbled them, and then reconcussed out here, which you normally probably would have concussed out here. I'm not sure of that, but who knows? Anyway, that's the difference between the red and the green. And the red is obviously spinning slower than the green. And I showed the red spinning. Now let me show you something else. Okay, got Mason again with me still. We jump to another shot here. This gives you a little idea of things quickly. This up at the top is the wave, which is a particle basically. And as it spins, it creates a wave because the particle itself has a magnetic field around it. And eventually heading towards the venturi, which is just like the nozzle of a hose. At this point, the light is atomic vapor, where the cursor is right now. And you can see the particles start to accelerate. And right here, it thinks it hit a stone wall, basically, because of the back reverse EMF, it's called, reverse electromotive force, which is just nothing more than a magnetic field backwards because of the bang. It's like, look at the energy increase. Do you see what I'm saying?
Right.
You see how much? Go ahead.
Yeah, even though they say every force has an equal and opposite reaction, so even the field itself reverses.
Yeah, oh yeah, absolutely. And you can see it very easily in some of the shots. Huge reverse field. And just recently they've been posting, well, we can see light moving forward and backward at the same time. That means we can go back in time. They're talking about the stuff I'm doing here. The field goes backwards, it's just bouncing the magnetism, boing, 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 backwards. That's all. It's nowhere near what they're thinking. No. Over here on the right are the Higgs fields. Now coming out of the venturi, which is right up here, so it all collects going through, again, the nails, literally nails at the venturi, and forcing the white fields to concuss with other white fields, exactly what they do at CERN. Only they do it head on. We don't have to bother with that. We make it do it sideways. Much more elegant. And it comes out right here. And we should be able to harvest that white energy because that's all we want. We don't want the black. But the black just starts jumping back in here right away. This is only like, I don't know, a bazillionth of a millimeter away. Now, what do the particles look like? This is what they look like right here. The green look exactly like the red. The blue are just too fast to see. Here's the blue. Now remember you said it takes a whole batch of pictures at one time?
Yes.
That's this right here, same thing. Here comes the blue. It's coming in real fast, slowing down. You see how the spin is slowing? This is a spin. And it's spinning to the right, which means it's drifting to the left. And you can see down by the bottom, you can see that it actually consists of the two dipoles. I have a shot where it's spread out a little better, so you can see up here it almost looks like there's only one. That's because it's going so fast, they look like one. And this is all shots at one time, right through the CMOS. Same thing you're talking about, I believe. Am I right, do you think?
Yeah, I believe so, especially just the same effect that you get whenever they do the quick shutter. And even if it's a car driving by, you'll get multiple images of that one car in the final photo. So it definitely makes sense. Okay,
this is good knowledge for me, because I'm not too good with this. But this is another really strange one right here. And this we will talk about at some future time, but it is the strangest thing I've ever seen. Now, this is the photon. I don't think we went through this yet. There's a red photon. Now, you see how it's polarized straight up and down? They will always be polarized straight up and down. If it was moving this way, it would still be straight up and down. If it was moving that way, still be straight up and down. Sideways, up and down. Doesn't matter.
And do we know why that is particularly? Or?
Because it spins like a top on the axis of the Earth. See the black and the white?
Yes, I see it.
It spins just like on a polar platform, basically, against the Earth's surface.
Okay.
All right, and then when the bottom, well, let me show you. Hold on, I can show you in detail what happens. All right, hold on. This is Rod. Accelerated the laser through whatever he was using, 2 nails, 3 nails. He was using glass. He was using all kinds of different things. He was using razor blades. He was using sewing needles. He was using all kinds of different diameters, materials. He's got one glass. It looks like a ripple going through there, like a bubble. I should show you that one. Anyway, this right here, that little spot, is the photon. The black is the muon, and the white is the electron neutrino. Those are both the two neutrinos. Now, that's the smallest units there are, or those two neutrinos, the smallest I can find, except for that oddball looking thing that I just showed you, Mason, that I said we'd talk about some other time. Because I don't know what to say about it. Well, I do know what to say, but I don't know if it's right, so let's just go with what's pretty easy here. And this is pretty easy. You can see it's the exact same thing as the red. Now, what do you see, though? You see that particle heading from right bottom up to the left. Okay, so big deal. Straight up and down to the Earth. You see the polarity straight up and down?
Yeah, I was going to say that you can see the, imaginary line almost, or invisible, not imaginary.
Straight up and down.
But it's still straight up and down, even though it follows that.
Spinning just like a top. You take a top and spin it, it stays straight up and down. If it's really spinning, these puppies are spinning. You saw the red spinning a minute ago. Did you see as I was scanning through that?
Yes, I did.
Unbelievable. Now, so what are we seeing here? This is all one shot, taking all those pictures. Now, so you got a strobe of pictures. This one shows this photon in a pretty good condition here. Well, what happened here? What's going on with that?
Is it losing energy?
Nope. It's gaining energy. The bottom front, you see the bottom front here?
Right.
At this point, it's not really energetic yet. Up here, it's because it's in the front. As it bashes into every other particles in front of it, it pushes and it starts to glow. And up here, it's really glowing. And it's going to push to the back, and the one up here will come to the front. See, you can't really see that there's a difference in energy here. but it's, if you had this with the highlights, you'd see extreme difference in the energies. This one is big and fluffy and glowy, and that one is...
I can see the shape difference. It's not as compact.
Yeah, and it's going to flip. It's right in the midst of flipping right now. And that's also called the muon wobble. That's why we saw your thing going like this, traveling through, you know what I'm saying?
Yeah, that makes sense.
All right, and it's coming from down here, and it's traveling sideways, and but it's straight up and down. That's the upspin and downspin they always talk about. Hold on a second.
Up so you can see it then.
Okay, good. And again, this is just brand new stuff, right off, hot off the press. And I don't know much about it, but I'm going to ask a bunch of questions. So this is Mason. He's going to be showing his screen, and I'm trying to think if I can make full screen. I guess this is good enough. Go ahead.
So this is one of the other images using the Venturi, but this one is where I used an infrared filter so that it cuts out most of the infrared light.
All right. And hold on a second.
Indigo purple.
All right, let me ask you a question. This, it's coming in from the bottom left?
Yes, that's the light source.
All right, and what's this thing doing here? And then the Venturi is at that gap?
Yes.
Okay. And you are looking down at that gap?
Yes, I had the phone on a tripod.
All right. And how wide is that gap?
Probably just about an inch or two. It's not much higher than the actual laser.
Well, I mean, where is there like a pin here and a pin here?
I'd have to go. I can't see your perspective on things because I'm sharing the screen.
Oh, okay. So,
yeah.
All right. Well, let's go to where you take your cursor and show me where the Venturi is and how it was constructed.
So the Venturi was basically the same two-nail system. I don't know if you can see this little crosshair here.
I just barely. Hold on. I can see where you are. Yeah, okay. I'm seeing it.
Yeah, so that's where the position of the actual nails are.
Okay.
And the laser source is down here.
All right.
So just off screen is where the actual point of light is. But they're right here. You just can't see it because the ISO is
all right. So right at the end of that little stem coming in is where the Venturi is, and then coming out of the Venturi is that ball.
Yes.
And that ball is like, it looks like something's like pushing past it, like vapor.
Yeah.
Right.
Here.
Yeah. Can you change the color of that cursor? Don't worry about it. Don't worry about it. Just, I can see, to me, anytime there's brightness, it means there's energy. And the brighter it is, the more energy there is. So we're coming through that Venturi, and that ball is, in my opinion, 100% white. It looks like to me.
Yeah. This one?
That's what I'm seeing.
Is it this one or this one? Oh, okay, this one, yeah.
The ball right there is like 100% white, and it's left a black behind somehow. And then it turns brilliant white there, while I assume at that point, I'm going to have to guess, it's reattaching. And there's an energy exchange when the white whacks into the black, because they do have an energy exchange. Of that, there's no doubt. That's what light's all about. Now, why? Well, it is strobing. Okay, let's think about it this way. Give me a second. I got to sip my tea as we think. All right. Let's think about it. Is it strobing that spot right behind that ball right here? Is that a strobe spot? In other words, is that ball actually not, is that ball actually there but we're not seeing it? Is that what I'm saying?
Which one? This one here or this one?
That one there. That ball coming through. If you keep going down, back the other way. Back the other way. Back. Just keep going back. No, the other way. The other way back.
Oh, this one.
Yeah. That's where the light is coming in from, correct?
Yes, correct.
All right. Then when it hits that black spot in between that and this ball right here,
Right.
that's where your venturi is, correct?
Yes,
All right.
correct.
Out of the venturi is squirting that ball. Would you agree with that?
Yes, I would agree with that. It looks like it's almost coalescing once it passes through the venturi.
It's completely round. It's completely round like a ball. And trailing off of that, I see on the bottom, there's like a vapor. And behind it, there is also like a vapor. Would you call this vapor back up in this area here? What would you call that?
I would definitely say it looks like vapor. It almost looks like steam being pushed in a direction, like colored steam.
You see the bluish tint to this? Right
Yes.
down here. You see it?
Yes, I can see it.
That's a higher energy level. Well, yeah, it's a higher energy level than the other colors. Now, why that thing is so brilliant in the middle is because it's basically a reverse nuclear explosion. It's an inward nuclear explosion. The white is getting slammed at by what's coming into it. It looks like to me. Yeah, the bigger you can make it, the better. Yeah, I'm seeing what that's what it looks like to me. It looks like to me that it's being swarmed by dark particles, and it's making that concussive white, and you can almost see like balls around it, forcing themselves in. Yeah, all around is surrounding. Whatever that energy field is, whether it's going inward against whatever that ball was, which to me was nothing but white matter, 100% white. However, at that point, it doesn't look like a big ball of whiteness because it just came through there. Now it's energy fields, which you don't really see, are concussing with all the energy fields in front of it, and they're coalescing into that ball, which is right here, and surrounding it. And just like, did you see the tether incident?
No, I'm unsure.
All right, here's what happened. In space, there is just nothing but a zillion particles. And they attached to this tether they put out there, thinking that it was a long strip. They were going to see if they could collect energy. And let's say it was 20 feet wide. It was a little strip of stuff, but it was 12 miles long. When they put it out, it was like I say, maybe, let's say 20 feet wide, tops. It collected so much white, like that white bright right there, because there was so much particles looking for dark matter, that it went a mile wide signature, like that thing right there. That could be 6 inches wide, and we're looking at it. It could be a mile wide because of all of the particles that are trying to find themselves back into the dark matter. Those are called Higgs fields, and I think we're seeing them like coming from the big ball, yeah, right down and they're whacking into that white particle, and it's whacking a bubble ahead of it. You see the bubble ahead of it?
Yeah.
That's because that particle is, yeah, exactly. It's engaging with the fields that are in front of it. And the fields behind it have almost turned like bubble and blue as it's moving forward. I'm not sure what that exactly means, but it is those those little round blue fields. You can see them pretty good now. Can you make it even bigger now?
Yeah, down here.
Yeah. There you go. You see those round fields? I'm circling them from here. I don't know. Yeah, there you go.
Yeah.
And they're surrounding that. Those are Higgs fields. And I showed you the Higgs fields on mine, right? They're all over the place. We got them on steroids. And it's almost, you know what? Drop that down a little bit.
This way?
No, the other way.
Okay.
Yeah, all right, that's good. No, don't go too far, a little back.
Oh, okay.
A little more. All right. Pretend this, that the light is coming in from up the top and down, which we know that's not the case, but let's pretend it is. That white particle blob is going to hit everything that has dark particles in it, and it's going to spray out a field of these dipole circular disks. You call them whatever you want. They're little round patterns. Let me share my screen. I gotta call that up, and I can show you Higgs fields on steroids. All right, hold on a second.
Gotcha.
All right, here we're going back to Rodney. I'm telling you, that guy was just unbelievable. I haven't heard from him in years. I just hope he's all right. But anyway, Rodney Warren just stumbled on this when he got his new Galaxy phone S3 in 2012. And we saw these same particles, and they were talking about Higgs fields. Here they are, and it just scads them. And we saw the same particles that they saw at FERMILAB. We saw everything that they saw, the muon, the electron neutrino, which is the black one and the white one. Anyway, and we were using light, which is this. Now, these circles are the Higgs fields. You saw before that white blob came in and hit whatever it hit, and we saw some white little those little blue circles, right?
Right.
You remember that. This is basically the same thing. This is coming out of the venturi, which has been separated from the black particles. They're gone. Now it's coming through, and you see the little black ones over in here?
Yeah, I can see those.
They're trying to dig in here right away. This is a splash into blackness. They got to be everywhere. I don't know. They got to be everywhere because they're hooking into the white ones. You see, look up here. Watch this little spray. It's coming up, and then it starts hooking up with a black one, and then it starts to make this circular pattern.
Wow.
Now, what is it?
It's interesting how you can actually see the fields directly, whereas I believe CERN had put out images of the Higgs boson fields, but they were just like graphics.
Yeah,
data.
Unbelievable what they put out compared to it's unbelievable what you put out, that green laser stuff with all those little fields. Yikes. That was that's stimulating. We're going to be looking at it now. Look at this. Light, this is the end spray where it's finally saying, all right, that's it, no more. You're gonna have to come back to what you started out as, is two particles hooked together. This one here, this purple one, it's not supposed to be here. It's pinched. You see this one right to the right of it here?
Yeah.
See how it's glowing? It's shoving this particle field, which is here, you can't see it, in between these two. It's just a mess right here. And they're ones, what I'm getting at, you can see all kinds of strange interactions when you know what to look for. That's an anomaly. They're all supposed to be coming through pretty green, pretty red. Mm-hmm. All right, but you see the Higgs? We could do this all day long. And it just keeps splashing through there. You don't even have to stop. It never stops. And as far as I'm concerned, that white is just raw electricity. As raw electricity. If you can harvest that white without collecting the black, which you can point that right at a receiving diode. It would enter that diode one way, and that's it. It's a singular way in, no coming back. And the white would be absorbed, and then you could turn it into whatever you want. It's all they do when they use a generator. Am I right?
Yeah, that's very true. That's why I never understood the whole concept of light just has no mass whatsoever. But when you use even just like the radiometer, for example, and you shine light at the panel, it starts. If something doesn't have mass, how is it able to act or put forces on other objects, visible or non-visible?
You know, the crazy thing is, I have one here. What you're talking about, Crookes radiometer.
Right.
And here's the deal with matter. Well, do you know about the dipole electron flood theory?
Yes, I read the paper.
Okay, so matter is just a double-sided particle. One of them's white, one of them's black. The black one has all the mass and no heat energy whatsoever. If you just had a ball of blackness, you would have absolute zero. All right, absolute zero doesn't mean just absolute zero temperature. It means absolute zero electrons. Because if you don't have any electrons, you don't have any heat. All right, that's what they are, is heat.
Right.
That's all electrons are, is heat. And they have no mass. And I agree with that. They have no mass, the white particle, but the black one has mass. And 1839, I believe, is the magic number that becomes stable. 1840, right in that area, which makes a proton. It's not just one. All right, the dipole electron flood theory, you said you read the paper. It's a ball, it's a little ball of particles. And every one of them is a little magnet, basically. It's a dipole. Dipole means a magnet. When they come together, there's two possibilities. When they come together, the black can separate from the white. We know this because we've seen it, we've done it. It either pushes all the black to the center, or at least pushes a little core of black to the center, and then surrounded by white. So it's one or the other. Now, if it pushes everything to the center of the black, all the white would crust around only black in the center. That's one dipole possibility. The other one is that you have the black in the center, and then you have a layer of white. Then you have another layer of black, like a layer cake. And the ones that are closest to the center are the blue. And the ones that are at the furthest from the center are the red. And in between is the green. Make sense to you?
Yes, it definitely makes sense. I actually watched the video where you showed the atomic explosions, like on a larger scale.
Yeah.
And that definitely helped me to understand what you meant by those waves, how the white comes in first. And, it's almost like that flash vaporization. And then the particles with mass come after and basically knock everything over.
Yeah, well, isn't that amazing? It's very slow motion, but that's exactly what does happen. Everything combustible. So what does combustible mean?
Able to be exploded or set on fire? Or reactive as
well, all right. Let's what is that? What exact frequency of light is hitting that house? We know it's only the white, but is the white got a frequency? Or is it just a ball of atomic vapor? I don't know. I don't know if it has. At that point, it doesn't seem to have anything other than energy. It doesn't move a damn thing. And of course, it doesn't mingle up with metals and so forth because they have no basic combustibility, like when you make metal, you burn off all the cheap stuff. What they're doing is hitting the house and the shingles and the curtains and the siding and all that stuff just vaporizes because it's being invaded by these white particles, just like this here. Now, I imagine if Rod put a piece of toilet paper or something from there, it might combust. I don't know.
Even how people use the, I think they call them solar death rays, where they take a giant lens and then concentrate the sun's light to basically crack like a rock even. They'll set up like a rock and then the heat from the sun itself will just like split it in half.
Oh yeah. I have a friend in Italy, Rogran, and he does it with multiple magnifying lenses.
Oh, okay.
All right, so he multiplies the lens and the distance and the aperture and the this and the that, and he gets it down to where he focuses it on a syringe tip that has a water bead coming out of the end.
Oh, wow.
All right, so he's got almost a micro-sized ball coming out of the end. Rogran's a pretty sharp guy. And he's got like a micro-sized ball of water coming out of the end with all of this extremely high energy, probably somewhere in the like this. And he's hitting that beam and focusing it into this hydrogen, water, it's H2O, hydrogen and oxygen. Now, hydrogen and oxygen, the crazy thing is they burn. I mean, you put hydrogen and oxygen gas together and hit it with a spark, you got an explosion, and I'm talking serious. So why are, when they together, they put out fires? You follow me?
Right. Is it because it's stable, or it's at the place that it wants to, like the particle wants to be, the same way that the white and the black, they always want to attach to each other, or the black wants to attach? Is it the same thing with water?
It has to be. There's some form of stability going on. Well, if you go by the standard atomic model, your H is a 1, and there's 2 of those, and your oxygen is a 6, and stability is an 8. So you got a 6, and you add 2 1s, you got an 8 stability. Now, you take H2 and O2, you got a 4. No, wait. You got a 12 and a 2. So you got a 14. And anyway, whatever ends up happening there, they all explode and combust and make an explosion that just is staggeringly loud. There's a video on where a teacher shows H2O2 in this one balloon, and H2O2 is a gas. It's mixed together in that balloon, and it's floating because hydrogen lifts the balloon. So it's floating there. He takes a little match and he goes up. He says, open your mouth, otherwise you might blow your eardrums out. And he touches the match to this thing and it exploded. The kids went insane. The explosion just shook the whole room. And what was left was water. It was a vapor. Water vapor was all that was left. And that's because the H2O2 in that balloon, H2O2, turns into H2O. And the other O combusted. That's why it always takes oxygen to have combustion. All right, you can't make something burn without oxygen. Won't burn. You ever consider that? This gets deep, man. This gets deep, deep, deep. Dipole electron flood.
I always think about how, sorry, not to cut you off.
No, that's okay.
Like, you see those space movies and Star Wars, and they're blowing up battleships, and I'm thinking to myself, there's no oxygen. That wouldn't happen unless it's the oxygen on the ship itself. But how is that explosion even existing in space.
Well, let me think. An explosion would go. You could have an explosion in space.
Right, but like the fiery ones with the special effects, like how you see in Star Wars, where the ship will be on fire in space.
Well, inside the ship, you could certainly have a fire.
No, yeah, of course.
But not.
I remember seeing this one scene from one of the recent ones where she's standing on the outside of the ship to go repair it, and there's a fire, and it's on the outside of the ship. She's in a spacesuit, and I'm like.
Well, if they were in the ionosphere, that might happen. In the ionosphere, it's over 3,000 degrees.
That's true. Yeah.
It could happen easily. Yeah, it could. They have to be in a certain place at a certain time. And if it was me, I'd say I don't want to be there when the sun's up coming at me. You put me in the shadows somewhere on the edge. That's fine. But you know what I'm saying? That gets hot. The sun really puts some beams out. So anyway, this is just staggering stuff, man. Hold on one second. But anyway, you understand the dipole electron flood theory.
Yes.
All right. Anything else we want to talk about here? We're seeing the particles. Yeah, I want to make one other statement. Coming in from the other side, as we saw when they started to compress, and we saw some particles light up just like this. Remember? That we hadn't seen before. All of a sudden they popped up like this. That's when they were being stimulated from the other side. It's the same field going in as it is coming out. You understand what I'm saying?
Yes.
When they are apart, they come back together. They come back to the same field they were when they went before. They make these circular patterns, and that's what we saw as it approached the Venturi. We had these exact same patterns. So what it was before, it came back to being again. This is after the Venturi. Hold on one second. Okay, this is the particles that CERN, Fermilab, Lawrence Livermore, all of them. The black with the glowy edge around it, which I've been showing, and the red that could get puffy and small, has no weight whatsoever, and that's exactly what they say. And the black has all the weight, and it's a fixed size, never gets bigger, never gets smaller, and has this glowy red edge around it. All right, so that's the fixed one. Never gets bigger, never gets smaller. This one here can get big, can get small, and it has virtually no weight whatsoever. And I can agree with all of that. And here's those particles we found when we excited the light and accelerated it. And Rod was able to do this with the CMOS. And this goes way back. And when I saw this, you see up here? Light is dark energy and matter in the vacuum of space. This was a video I did in about, 2013, 2014. Because I found it and nobody would listen to me. So I said, well, I'll just put a video up and they'll see it. Nobody cared. So anyway, that was Fermilab right there. We paid billions and billions of dollars. And I sent this to them and they said, no, you're crazy. Well, I ended up going to the University of Geneva. I think I told you that about 16 times. And they eventually said, yeah, you're right. You can see these particles with CMOS, and they are doing that now. And here's the particles in the front. You see these little particles? Hold on one second. I was out of focus, but they could hear our conversation. Now I'm back in action. Now, these little particles in front of the one that's coming forward, they're making the one coming forward glow. All right, you understand what I'm saying? That one there is banging into these fields. The other one is getting small because it's hiding behind the black. When that gets a little bit bigger, it's going to flip to the back, and this one's going to come to the front. You good with that?
Yep.
You understand why?
So is it because when that particle gains more of the energy, or as you're saying, the white, then it reverses, or is it? It
pushes back. It will flop. It'll spin. This is why they spin. Okay. This is why particles spin. I showed you the spin before. This is why they spin, is because one particle charges up until the other one has no charge, and it jumps to the front and this jumps to the back. This discharges as that one charges, and then they flip-flop, 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 flip-flop. That's what they see. They call it the muon wobble. I agree with that 100%. Now, what did we do with that light at the Venturi? Well, we see it's totally attached, and they do not disattach themselves until you either hit them head on, like they do at the colliders, or into Cherenkov radiation using high accelerated particles in hitting heavy water. This is from CERN and Fermilab. The muon neutrino is the black ball. The electron neutrino here is the white ball, black and white. The muon goes on its way as a black ball, and the electron turns into an electron shower. This is what happened with ours. The black turned into a muon neutrino all by itself. All by itself. Lonesome me, all by myself. I can't find a white little particle. Well, what happens to them, I don't know, but I don't think they jumped over here and re-entangled. You follow me?
Yeah. So only life out here for a particle.
They stayed on this side. As far as I'm concerned, they stayed over here and reattached to something over here. You can see them trying to reattach here, anywhere they can dig in. But where you don't see them, they're still here. They're all over the place, because you can tell, because they're all jumping in. And right about here, they said, that's it, we're coming. You guys are going too slow. We can now grab a hold of you. And they all start to attach right out here. Up to here, we got raw electricity. I see no reason whatsoever we shouldn't be able to harvest that and use that for free energy. That's the particle accelerating, that's the particle. And here's the ones I'm talking about. The fields are all here. You don't see them. We don't see those. You don't see them. They're coming.
Yeah.
They're coming just like this one. The only reason you see this one in the middle, Mason, is because it's being accelerated. So it's gaining energy rather than just light. Light appears to move in the medium it's in without displaying any big energetic value. The particle, you see this one I'm going with right here?
Yeah.
You see how brilliant that is? You see how brilliant these are?
Yeah.
Here they're not even there. You don't even see them. I'm telling you, this the same one like this is coming forward. One here, one here, one here, one here. They're all over coming forward. You just can't see them because they don't have enough energy to display. You follow me now?
That makes sense, because I know even with how CMOS works, it converts the light into the electrical signal, but only past a certain threshold, like past a certain energy threshold, right?
Well, that, yes, and there is energy being transferred, coming forward and making these particles glow, but more likely is the glow coming backwards, which they say, oh, we can see these particles going backwards. Can you see these real lines way over this side?
Yes, I can see those.
That's the reverse EMF, electromotive force. And when it goes backwards in those very compacted lines, it means you got a hell of a lot of energy going backwards, which normally you wouldn't have that. The only reason you have it is because of what happened here at the Venturi. It's literally a subatomic nuclear explosion. The black is separated from the white. When it does that, it seems to want to own its own space. And they normally sort of hang around together without too much of an interaction. But once they separate like that, you get the explosion. This is literally, no question whatsoever, this is a subatomic, which means what? Smaller than atoms, right?
Yeah.
Subatomic, smaller than atoms, nuclear, which means what? Parts of the nucleus, right?
Yeah.
Because the light is, in my model, is just nothing more than dipoles, which make up the nucleus, which make up everything. So it's smaller than atoms, because we're only using light, subatomic, nuclear, because they are nuclear particles. Explosion, because they're breaking apart.
It's funny because even until you pointed it out, the lines from the EMF,
Yeah.
I didn't notice how they were going all the way back to the actual light source, or not the light source, but where it's at the Venturi, and it's so collected.
Yeah, basically. And this is nothing more than an atomic bomb. Now, what else is it that is stunning? Well, it's fission and fusion. All right, these particles were attached together, which means when they're glued together solid like that, and they are tight, they are tighter than hell. It's called the strong nuclear, because these are nuclear particles, the strong nuclear force. That means they are held together in a nuclear bond that is extremely strong. And in light, it's even stronger.
Right.
Now, here, though, when we put it through the Venturi, it ripped the white away because the Venturi is too small, and the black just kept slapping. The white kept shooting. Somewhere, these other black particles have to exist just hanging around. They have to. Where do they come from? They're reattaching to the white. I always felt like everything had a partner. Where's the black coming from? It didn't jump from the back here to the front, right? I wouldn't go with that, would you?
No, I wouldn't either. Like you said, as it's just occupying space, it has me wondering if I don't know if you know about the neutrino detector they're building over in Japan, I believe it is.
I know about all of them, yeah. They got the deep underground nuclear one over in the Fermilab. They got one going on at CERN. They got them everywhere. And they're looking for neutrinos. Here they are. Here it is, muon neutrino, electron neutrino. We found these in 2013, 2014. And I sent this and all my information to CERN and to Fermilab, right here, these particles. I said, we found your particles using light. And boy, I'll tell you, that was not received well. And so I ended up going to, as I told you, University of Geneva, and I said, hey, these are the particles. I said, address it. I went through Coursera just like you're doing now. And I talked to the professors, and I actually discussed, I didn't actually talk to them, but I sent back and forth, and it was very detailed in my explanation. And I have all the details. I have all the, this is the proof. And their original one was you can't use CMOS, if something's wrong, And then when they realized, yes, CMOS was for this, everything changed. So, but I was surprised they didn't want to go any further with this. And the reason is, the only thing I can take from this is there's a couple of possibilities. One is it's just job protection, because in my mind, the whole idea of what they're doing is getting down to these particles. These are the particles they want to find right here. Those are the ones, and what's their energy levels, and how do they spin, and how do they reform, and how do you use them in half-lives? Because in my model, every proton is 1839, and every neutron is 1840 of these dipoles. So when you get into isotopes, you've got hundreds of thousands, millions of particles to have half-lives. They say, oh, it has got 22 isotopes. No. Most of them have at least 2, 4, 6, 8,000 isotopes, minimum. So they can only see the ones that they can see. The ones that they can't see are being used by enzymes to build chemistry, to do nucleophilic invasion and substitution of biology. It's all related to dipole electron flood theory. It does biology, it does chemistry, it does heat, it does light. It's all, and the stuff you're showing shows these particles doing what they should do, coalescing as they should, giving off the vibrations of energy that you would expect, and you know, I think you've got a lot of stuff you can show, and I got a feeling you're going to be showing a lot more, my friend, because what you're doing is fabulous. And this led the way, Rod, no question. And I started doing the same stuff he was doing here, but there's no competing with somebody who wants to spend 1,000 hours. I had a million things I was doing, but I was also spending a lot of time on this because to understand it, he just sent the pictures. He was fabulous at doing the experiments, but he was looking for something else in the light. He was looking for there might be life within the light, and I do believe that is true. In the ancient texts talk about the life is in the light. We come from the light. We are children of the light. And everything was about light in some of these ancient texts. Very, very stunning. But that was his goal, was to see, and he found some things that I can't dismiss. They sure look like it. And but I didn't want to get down that rabbit hole because, you know, I was in swampy waters already. Once you start saying I found Jesus in the light, then you know what I'm saying?
They take you away in a nice.
Well, you know, I think that might be what happened to Rod. I'm not kidding you. I'm not kidding you. He's in Australia, and his nephew was in New Zealand, and neither one of them have I heard back from in years. And I know that Rod was being attacked by everybody, and I was here too. They used to tell me the same thing. They said, "You got to see somebody. You really need to see somebody." And I said, "Yeah, I need to see somebody that knows what they're doing. You people are just lost. You don't care about anything." They said, if this was all real, they'd already know about it. You're just wasting your time. You're an idiot. You're a fool. All of this stuff about nonsense about rocks being alive once, and you know, I mean, really, I went through this for many years. And the same people that dismissed me back then, just still not interested. But when I show the stuff I show now, they realize it's true. I still just, you know, I don't know what it is. Whether it's that they want to stick with that feeling, or is it that they just really don't have an interest? I can't see not having an interest, but.
I think honestly, relating to what you said earlier, even just job security, if they figure that, wow, just some old Joe Schmo, for lack of a better term, can figure this out at home, and we're receiving billions of dollars in funding to get the same results, or sometimes worse results, it honestly, I feel it does boil down to that.
Some of the things that they're doing might be causing one hell of a terrible problem. And that's at Yellowstone. I was just doing a video before, you know, our meeting. They just released some information on that, and yikes, is all I can say. I'll be having that video up hopefully sometime today. It's getting late. And listen, what we need to do is to get back together with some more of this stuff. I don't even know how to